These two daily works are both, broadly speaking, about homomorphisms, right? And what can homomorphisms tell us about the structure of groups? So daily work number 21 is mostly just about homomorphisms themselves and getting our heads around the basic definitions and properties. 22 is more about those applications and the first isomorphism theorem. So, first survey question. Suppose we have a homomorphism from G to H. Which one of these things does not have to be true? Identity to identity, inverses to inverses, phi preserves orders, and the image is a subgroup of H. Which one's not necessarily true? C, that phi preserves the orders of elements. What, in fact, do we know about how homomorphisms behave with respect to order? The order of the image is not equal to the order of G, but is a factor of the order of G. We talked about that one in our last class. Great. So that's for that answer. How about the second one? If G is a non-trivial group, is it possible for there to be exactly one homomorphism from G to G? Which answer did you say? A, yes, if G is simple. No, because G has as many homomorphisms as elements. No, G has at least two. So first of all, when I say non-trivial group here, what do I mean? It's not necessarily an infinite group.
Maybe.
How many elements does a non-trivial group have? Or let me ask it that way. How many elements does a trivial group have? One. So a non-trivial group has, at least two elements in it, right? Okay. All right. So which one do we think? Maybe we should take a quick poll. For a second, let's talk about what it means for G to be a simple group. What's that definition?
The only subgroups are the group itself and a trivial group.
Yeah. The only word I'd add to that is the word normal. The only normal subgroups are trivial group, which is just the identity, and the whole group itself. Okay? So that's what the word simple means. So what's an example of a simple group, by the way? Are there any cyclic groups that are simple? Z2? Yeah, Z2 is a good example, right? The only subgroups, period, of Z2 are the whole group and the trivial subgroup, right? Because any other subgroup would have to have an order of what? Lagrange's theorem. 1 or 2, right? But the only subsets of order 1 and 2 here are, the whole group and the trivial group, except for the set that just has the number 1 in it, which wouldn't be a subgroup at all. Okay, right. So, all right. So if G is a simple group, is it true there's only one homomorphism from G to itself? What is that homomorphism? If you answered A, what is this exactly one homomorphism from G to itself? But what is the function that takes this group to itself? That would be the only one way to do that.
5x to x.
Phi of x equals x, the identity function. Remember, that's always a homomorphism from a group to itself. The identity, for any group at all, right? Regardless of whether it's simple. Okay. Is there another homomorphism from a group to itself besides the one that is the identity?
Is it 5x to 0?
The 5x is equal to 0, or identity element, right, for all x. These two homomorphisms always exist from any group to itself, right? The trivial homomorphism that sends everything to the identity, and the identity homomorphism that sends everything to itself. Right? Those two homomorphisms exist for every single group. And as long as G is not a trivial group, they're different from one another. But that means, is it possible for there to be exactly one homomorphism from a group to itself? So how do you want to answer this question? Yeah. Every group has at least two homomorphisms to itself. By the way, if you like terminology, and who doesn't, a homomorphism from a group to itself is called an endomorphism. So if you want to impress your friends, as though you don't already do that as a math major, the set of endomorphisms, sometimes called end of G. It's not a group, because they're not necessarily invertible. They don't necessarily have inverses. But the set of endomorphisms always at least has two elements, the identity function and the trivial function. Okay, last question on this one. The homomorphism from Z6 to Z6 defined by multiplication by 3. Which of these is not a part of the kernel?
B.
B. Why not?
Because 3 times 1 is 3, and that is not 0, not 6.
Yes, very good. 3 times 1 is not congruent to 0 mod 6, so 1 does not belong to the kernel. But you can check that the other 3 choices all do, right? I multiply 0, 2, or 4 by 3. The result is 0 mod 6. So what is the kernel of this homomorphism? 0, 2, and 4. Great. And any of the other elements, i.e. 1, 3, and 5, those are not getting sent to the identity. Okay, great. So for the first problem, we have a group of finite order. And we have a normal subgroup N. Which of these things does not have to be true? There is a homomorphism a homomorphism into G whose image is N. There's a homomorphism out of G whose kernel is N. The cosets in N of G form a group, and the order of the factor group divides the order of G. Which one of these 4 things is not necessarily true? Anyone have an answer besides A?
B.
B?
I don't know. Devil's advocate.
That was going to be one of those two. I appreciate the devil's advocacy. But yes, so I agree with A. There exists a homomorphism into G. There exists a homomorphism into G whose image is that normal subgroup. By the way, how do we know that's not necessarily true? What do we know about the image of a homomorphism? What kind of a group, what kind of a subgroup is it? Well, so the first isomorphism theorem tells me that it's isomorphic to the factor group of G by the kernel of this homomorphism, yes. But what is it? Maybe another question is, what is it not? What is the image of a homomorphism not necessarily? Not necessarily normal. The image of that's the one place where normality is not guaranteed in this process, right? So we don't know for sure that every normal subgroup arises as the image of a homomorphism into my group. But we do know that every normal subgroup arises as the kernel of a homomorphism out of my group. So every normal subgroup is the kernel of a homomorphism, and every kernel of a homomorphism out of a group is a normal subgroup of that group. Okay, so that's A for the first question. For the second, suppose that I have a homomorphism and it's coming out of a simple group. So if G is simple, according to our definition of simple we talked about a minute ago, which of A, B, or C cannot be true? Uh-oh. So if G is a simple group and we have a homomorphism coming out of G, why can it not be true that phi is neither trivial nor one-to-one? So in other words, what you're claiming is that phi must either be trivial or must be one-to-one. How do we know? Yeah. So yeah, I agree that if G is a simple group, then any homomorphism coming out of this group has to either be the trivial homomorphism or a one-to-one homomorphism. Because why? What's the link? It's the kernel. What do we know about the kernel? It's a subgroup of G, right? But what kind of a subgroup is it?
Normal.
It's a normal subgroup, for sure. And if G is simple, that means that there's only 2 choices for what this kernel can be. What are those 2 choices? The trivial subgroup or
The group itself.
the whole group. So tell me, if the kernel is the whole group G, then what is the homomorphism phi? What is it doing?
X.
Yeah?
X.
Quite. So remember, what is kernel? What does kernel mean?
It sends it to the identity. So
It's
the
what's getting sent to the identity, right? So if the kernel is all of G, it means that all of G is getting sent to the identity element of H. In other words, phi of little g would be equal to E for all G and G. And so in that case, phi is the trivial homomorphism. And then the other piece of the puzzle is, Caitlin, what you were saying, I think, was Caitlin? Kelly, that if the kernel is the trivial subgroup, what does that tell me about phi? Phi is one-to-one. In a way, the kernel of a homomorphism is a measurement of how one-to-one it is or is not, right? Because according to the first isomorphism theorem, all of the elements of G are getting mapped to H, and they bring all of their coset partners with them, right? So however many elements are in my coset, all of those elements are going to get mapped to the same place as I map by this homomorphism. So if my kernel is trivial, consists only of one element, then every one element in G is getting mapped to exactly one element in H, and every different one element is getting mapped to different one elements of H. Right? So when the kernel is trivial, our function becomes one-to-one. But if my kernel has, I don't know, 7 elements in it, that means all 7 of my coset partners are going to the same place that I'm going. So I have a 7-to-1 function. Right? And according to the first isomorphism theorem, that's true then for every element in my group, is bringing 6 other elements along with it and going to the same destination. But then that would mean that we would not have a 1-to-1 function in that case, because 7 different things are going to one same location. So kernel being trivial subgroup means that this is a 1-to-1 function. So if G is simple, the only choices for a homomorphism out of G are the trivial homomorphism or a 1-to-1 homomorphism, because the only choices for the kernel are the trivial subgroup and the whole subgroup. Whew. Last question. So if I have a normal subgroup N of G, how does the first isomorphism theorem help me to understand the factor group? Which of these 4 options? It says that the factor group is isomorphic to the kernel of phi, the factor group is isomorphic to the image of phi, the factor group is isomorphic to G, the factor group is isomorphic to N. Which of these is a faithful
B.
recollection? It's B. Yep. It's the image of phi that's isomorphic to the factor group. So instead of racking our brains about cosets, we can instead think about the homomorphism phi. What is its image? And that image will be isomorphic to the factor group. All right, so real quick, how do I find the order of an element in a factor group? There's 2 ways to do it. One of them, so the element here I'm talking about is 4H, where H is this subgroup that's listed here. So the quick way to do it is just to try testing what is the second power of the element 4H. So what am I going to get here? And 4 times 4, that's 16. But what's special about the number 16? It's an element of H. So when I take the coset of 16, what am I going to get? If I multiply all the elements in this subgroup by 16, I'm going to get all the elements of this subgroup again, because 16 was already in the subgroup, and the subgroup has the closure property. Right? So the very quickest way to do a problem like this, and it certainly works when the order is small, is just to try taking powers of the element that we're looking at. And now that I've gotten this to be H, what role does H play in the factor group, G mod H? What special status does H have? In the factor group, H is another name for the identity. And so now that I've found that the second power is equal to the identity, what do I conclude the order of 4H is? Order is 2. Yeah. That's probably the quickest way to do this. And given our time constraints, I'm not going to recommend a different one. That's more sophisticated. We maybe have time for one more question. So in question 2, we're sort of thinking through examples of homomorphisms. And part C asks us to try to come up with an example of a 1-to-1 homomorphism that's not necessarily an isomorphism. So if I have a homomorphism that's 1-to-1, what's the only property that separates that from necessarily being an isomorphism? Onto. So let's try to find an example of a homomorphism that's 1-to-1 but not onto. What's the easiest way for a function? Let's think about just set functions for a minute. What's the easiest way to make sure that a function from one set to another set cannot be onto? So the easiest way to make a function not onto is to have a function from a smaller finite set to a larger finite set.
So like
Right?
Z8 to Z10.
Z8 to Z10. If I can make a homomorphism from Z8 to Z10, then it cannot be onto. How do I make a homomorphism from Z8 to Z10? This is where it gets a little challenging. Let's get smaller numbers for a second. Let's do Z2 to Z3. I can do Z2 to Z3. So I know now this cannot be onto, but can it be a homomorphism?
Yes.
Okay, how do I make it a homomorphism? I got to send 0 to 0. Where do I send 1?
2.
But then 1 plus 1 is 0 on this side. 2 plus 2 on this side is 1. Uh-oh, problem. Let's put on our galaxy brain for a second. The image has to be a subgroup of Z3. What are the subgroups of Z3?
The identity.
Identity, just trivial subgroup, and
0, 1.
and the whole group. Because the order of Z3 is 3, any of its subgroups have to have order 1 or order... We can't have a subgroup of Z3 that has order 2 because Lagrange's theorem. Right? So my only option, actually, is to send 1 to 0.
So
But that doesn't work because it's not 1 to 1.
maybe Z4.
How about Z4? Now we're going to have more options. Right. Now where can I send 1? If I send 1 to 2 this time, now 1 plus 1 is 0, 2 plus 2 is 0, and 0 goes to 0, so the homomorphism property is satisfied. And the image is a subgroup. The image of phi is the subgroup 0, 2. That all looks good. What's the kernel? It's just the identity element, which is what we wanted for a one-to-one homomorphism, right? One-to-one means the kernel is trivial. So yes, here's an example of a homomorphism from one group to another group, which is one-to-one, but it's not an isomorphism because it's not onto. One-to-one homomorphisms are nice still. We sometimes call them inclusions, because what it does is it shows that there is a subgroup of Z4, namely the image, that is isomorphic to Z2. We're finding a copy of Z2 inside of Z4, up to isomorphism. But Z2 and Z4 themselves are not isomorphic. It's just an isomorphism onto its image, not onto the whole group.